Hello, we're Chris Virogs from the University of Florida and Daniel Zoe from Reed College. And we'd like to present our work on the coalescing particles on a cycle graph. As part of our talk, we'll give a basic introduction to the idea of a coalescing walk and present a couple examples of the coalescing walk on an interval, and the coalescing walk on a cycle. Then we'll present some simulations related to coalescing walks on a cycle and which will lead us to our main theorem. We'll then prove our main theorem and then discuss a variation of the problem of the coalescing walk on a cycle, the annihilating walk on a cycle. We'll then present our ongoing and future work. The general idea of a coalescing walk is this. We're given a state space S and a transition function P on the state space S. At time 0, we place a finite number of particles at distinct elements of S, and at each time t greater than or equal to 1, we pick a particle randomly. We then move that particle according to the transition function to a new state, and if the randomly sampled particle moves to a state that's occupied by a particle, we simply combine both particles into a single particle at the new state. An example of a coalescing walk is this, the coalescing walk on an interval. In the coalescing walk on an interval, we denote the graph IN to be the set, to be the graph with the vertex set 0, 1, all the way up to n, and the edge set 0, 1, 1, 2, all the way up to n minus 1 to n. Note that the vertex n is not connected to the vertex 0 on the graph IN. At time 0, we place a particle at each vertex of IN, and we'll say that a vertex V is occupied if there's a particle at V. Then at each time step t is greater than or equal to 1, we'll choose an occupied vertex V from the set 1 through n. Note that we'll never choose the vertex 0, and move the particle at the vertex V from the vertex V to the vertex V minus 1, combining it with any pre-existing particle at V minus 1 into a single particle. Note that eventually all particles will coalesce into a single particle at vertex 0. An illustration of this process is shown here for n equals 3, which means we have 4 particles. At the 0th time step, we have 4 particles initialized at each vertex of the graph. And at the first time step, we randomly pick a particle from the vertices. We randomly pick an occupied vertex from 1 to 3. In this case, we randomly chose the vertex 2, and we move the particle at vertex 2 from the vertex 2 to vertex 1. Since there was already a particle at vertex 1, we simply combine the 2 particles into a single particle at vertex 1. Again, for t equals 2, we randomly select an occupied vertex from 1 to 3. In this case, we randomly chose the vertex 3, and we move the particle at vertex 3 to vertex 2. As shown here. This process continues for the next few time steps until all particles coalesce into a single particle at the 0th vertex. We'll let tau n denote the time it takes for all particles to coalesce on the interval IN. There's been some previous work done on this problem by Michael Larson and Russell Lyons. In a paper of theirs, they show that the expected value of tau n is given by this equation over here. And they show that the variance of tau n is bounded by this expression given here. These results were proven, and they were obtained through an analysis of generating functions. We'll now consider a variation of the coalescing walk on an interval, the coalescing walk on a cycle. In the coalescing walk on a cycle, we'll let Cn denote the graph with vertex set 0, 1, all the way up to n minus 1, and the edge set consisting of pairs of i's and j's such that I and j differ by 1 modulo n. Note that the edge set is essentially the same as the edge set for the coalescing walk on an interval. However, in this case, the n minus 1th edge is n minus 1th vertex is connected to the 0th vertex to form a cycle. Then at time 0, we place a particle at each vertex of Cn, And then at each time step t is greater than or equal to 1, we'll randomly select the occupied vertex v and move the particle from vertex v to the vertex v plus 1 mod n, combining it with any pre-existing particle at v plus 1 mod n into a single particle. An illustration of this process is shown here. For t equals 0, we have a particle at each vertex of the cycle graph. Then at t equals 1, we will randomly select one of the occupied vertices. In this case, we chose 1 and move the particle 1 plus 1 mod n, or vertex 2, combining it with the particle at vertex 2. This process continues for several steps until all particles coalesce into a single particle, in this case at vertex 3. Note that the coalescing walk on a cycle is essentially the same as the coalescing walk on an interval. However, in this case, the first edge and the first vertex and the last vertex are connected to form a cycle. We define the coalescence time for the n cycle to be the time it takes for all particles on the n cycle to coalesce. We'll now denote the coalescence time for the n cycle to be tau n. There's been some previous work done regarding the coalescence time for the coalescing walk on the n cycle. In the master's thesis of Patrick Dekiel, there were some computer simulations that were run, and Dekiel estimated that the expected value of tau n scales according to 0.5 times n squared asymptotically, and that the variance of tau n scales according to 0.05 times n to the fourth asymptotically. Note that these approximations say nothing about the other coefficients of the polynomial scaling of the expectation value of tau and the variance of tau n. These are simply approximations for the leading coefficients for the expected value of tau n and the variance of tau n. This leads us to our main problem. We want to find out what the expected coalescence time for the coalescing walk on the n cycle is. We first started by running some computer simulations. We estimated the expected time to coalescence for different numbers of small numbers of vertices for the n cycle. And we found that the expected time for the n cycle, expected coalescence time for the n cycle is the n minus 1th triangular number. That is, the expected value of tau n is equal to n times n minus 1 over 2.
To prove that statement, we proved a significantly stronger theorem. And to introduce the main theorem, we will first introduce a method to describe different particle states on the n cycle by looking at the distances between consecutive particles. And by consecutive here, I mean counterclockwise. We look at Li, the distance between particle I and the next counterclockwise consecutive particle. For example, L1 here is the distance between particle 1 and particle 2. L2 is the distance between particle 2 and particle 3, and similarly, L3 is the distance between particle 3 and particle 1. By writing the particle distribution as a tuple of the L's, L1, L2, L3, we can describe the particle state. Looking at this method of describing particle states, we make the following observations. First of all the L's sum up to n. This is because we start at 1 and we always end at particle 1. Observation 2. When we move a particle I, we decrease Li by 1 and increase Li minus 1 by 1. For example, if we move particle 2, we decrease the distance between particle 2 and particle 3, but at the same time, we increase the distance between particle 1 and particle 2. And the third observation is that when the system ends, there's only one particle left. So L1 is the distance between particle 1 and the next counterclockwise particle 1. So L1 is just n. So now we introduce the main theorem of this talk. First, we define a function s to be the sum of all integers from 0 all the way up to x. Theorem 1, the expected stopping time for different particle states. We define tau to be the time it takes for all particles on an n cycle, starting at the k particle distribution of L1 to Lk to coalesce. From here on, we will refer to tau as the stopping time. Then the expected value of tau is Sn minus the sum of all the SLJs. With algebraic manipulation, this theorem implies that the expected value of tau is the sum of the product of distinct lengths Li and Lj. So I would like to give an example of that theorem being used. Here we have the 4 cycle and a 2-particle distribution on the 4 cycle. The theorem states that the expected value of tau is the sum of Li Lj's for distinct I and j from 1 to 2. Note that L1 is equal to L2 equals 2. So the expected value of tau is just L1 times L2, which is 4. And the second example, which is also the previous diagram, we look at the 3-particle distribution, on the 5 cycle. Note that the expected value of tau here is L1 L2 plus L1 L3 plus L2 L3. And when we input the values of L1, L2, and L3 in it, we get that the expected value of tau is 8. And I would like to present why we prove this theorem, because this theorem presents a solution to the original problem with this corollary. The corollary is that the coalescing walk on the n cycle, where a particle occupies each vertex, has expected coalescing time. The expected value of tau n equals half n minus 1. And the proof is very simple. You just let L1 equals L2 all the way to Ln all equal 1. And then when we use the formula, the result follows. Now let us prove the original theorem, theorem 1. And to do this, we would like to introduce a concept from probability theory, the martingale. A martingale is a sequence of random variables xn where the expected value of xn, given the history of the process, the expected value of xn plus 1, given the history of the process, is just xn, the previous state. The reason we would like to introduce the concept of the martingale is so that we can use the many theorems proven on martingales, specifically the optional stopping theorem. Now let us introduce the lemma. We first define a random variable mt equals SL1 plus SL2 all the way to SLK minus t. Note that this is a random variable of t, time. Since L1 to LK, the lengths change as time goes on. The reason this is difficult and the model is difficult is that as time goes on, the number of particles in the system can change, so k can change, but the result stays the same. And we would like to prove that this sequence of random variables, the sequence of mt, is a martingale. And our proof is as follows. Assume we are at time t. For the next time step, we examine the behavior of the length Li. There are 3 possibilities. First one is that particle I is moved, which occurs with probability 1 over k. Here, Li is decreased by 1. If particle I minus 1 is moved, which also occurs with probability 1 minus k, or 1 over k, Li is increased by 1. If neither of these particles are moved, and one of the other particles are chosen, which occurs with probability k minus 2 over k, then Li does not change. Thus, we can use this to calculate the expected value of SLI at time t plus 1, and we will find that it is SLI plus 1 over k. With some further calculations, we will find that the expected value of mt plus 1, given the history of the process, is just mt. So the sequence of the mt's is a martingale. And this leads us to a corollary where we apply the optional stopping theorem. Corollary is that the expected value of m0 equals the expected value of m tau. By a version of the optional stopping theorem, the following conditions are sufficient. The first one is that the sequence of m tau is a discrete time martingale with stopping time tau. We prove this in the lemma. Condition 2. The expected value of tau is finite. This is true since n consecutive moves of the same particle will always end the cycle, since it goes around the cycle and coalesces with all the particles. Hence, the probability that tau equals t decreases at least geometrically as t increases, so the expected value of tau cannot be infinite. The third condition is that the expected value of the absolute value of martingale increments is bounded upwards by some constant c. Note that we reach our maximum value of the absolute value of mt plus 1 minus mt when we decrease the maximum possible length, which is n minus 1, and we increase the smallest possible length, which is 1. Hence, the absolute value of mt plus 1 minus mt is less or equal to n minus 2, and therefore the expected value of the absolute value is also less or equal to n minus 2. And since n minus 2 is a constant, this condition is satisfied too. Therefore, by this version of the optional stopping theorem, the expected value of m0 is the expected value of mt. And this leads us to the easy proof of our main theorem. Note that at time 0, we just have our original L1 to Lk. So the expected value of m0 is just the sum of all the SL1, SL2 all the way to SLk. And note that at time tau, we have one length, L1 equals n. So the expected value of m tau is just Sn minus the expected value of tau. Therefore, the expected value of tau is just Sn minus the sum of all the SLJs, and we are done. Now I'd like to introduce a generalization of theorem 1, the p-coalescing walk. We slightly alter the coalescing walk on the cycle such that at each time step, we first choose an occupied vertex v. With probability p, move the particle at vertex v to v plus 1, so we move it counterclockwise. And with probability 1 minus p, we move it to v minus 1, which is clockwise. If there is a pre-existing particle at the destination, we combine the two into one particle, just as all our previous coalescing walks have done. We denote the system the p-coalescing walk. Note that the original coalescing walk that we have discussed for most of this presentation occurs when p equals 1. So this is a generalization of our previous coalescing walk. And we would like to prove our main theorem on the p-coalescing walk too. We look at the expected stopping time for different particle states. And then we would like to prove the exact same statement, that the expected value of tau is Sn minus the sum of all the SLJs. Note that in the previous proof, the only place where we actually introduced how the system works, how the cycle works, is proving that MT, the sequence of empties, is the Lamartine. Note that when we move counterclockwise, the expected value of MT plus 1, given the history of the process, is MT from the original proof. And a parallel argument will show that the same thing occurs when we move clockwise. So for probability 1 minus p. Thus, the expected value of mt plus 1, given the history of the process, is just p times mt plus 1 minus p times mt, which is mt. So the sequence of mt is still a martingale, and this theorem is proved too.
We'd now like to discuss a variation of this problem, the annihilating walk on a cycle. Let Cn denote the end cycle, and at time 0, we'll place one particle at each vertex of Cn as before. At each time step t is greater than or equal to 1, we'll randomly sample an occupied vertex v of Cn and move the particle at vertex v to the vertex v plus 1 mod n. However, for the annihilating walk on a cycle, we'll instead of combining the particle we move from vertex v with the particle at vertex v plus 1 mod n, we'll simply delete both the pre-existing particle at v plus 1 mod n and the randomly sampled particle if there is a pre-existing particle at v plus 1 mod n. Note that eventually there will be either 0 particles left on Cn if n is even, and exactly 1 particle left on Cn if n is odd. Here's an annihilating walk shown for n equals 4. Initially, all vertices of the cycle graph are filled. And then at the first time step, we move the particle from at the top vertex 1 step counterclockwise to the particle at the left vertex. Since there's to the vertex 1 step counterclockwise to the vertex on the left. However, since there's already a particle at the left vertex here, instead of combining them together at the left vertex, we'll simply delete both of them as shown here. And then at t equals 2, we move the particle from the bottom vertex to the particle at the right vertex, deleting both. So we'll now define the annihilation time for the end cycle to be the time it takes until there's at most 1 particle left on the end cycle for an annihilating walk. And then we'll denote the annihilation time for the end cycle by tau Na. We have a proof of a theorem, which is that if n is even, then the expected value of tau Na is equal to n over 2 squared. This leads us to our future and ongoing work. We've calculated the expected value of the coalescence time for the coalescing walk on the end cycle. However, we'd like to know more about the distribution of the coalescence time. So we're currently investigating the second and higher order moments of the coalescence time for the coalescing walk on the end cycle. We've also found the expected value of the annihilation time for the annihilating walk on the end cycle when n is even. However, we're not so sure about what the expected value of the annihilation time is when n is odd. We've run some simulations to estimate the expected value of the annihilation time when n is odd. However, we haven't found a pattern in the different values of the annihilation time for odd n thus far. Another problem that we're currently looking at is what we like to look at are finding the second higher order moments of the annihilation time for the annihilating walk on the end cycle when n is for both odd and even n. This concludes our talk, and we would like to thank you all for listening.